This is the video for Part 1 of Chapter 15, Geometric Constructions. The mathematics of the ancient Greeks was centered around geometry. One major focus of the subject involved geometric constructions using only a straight edge and a compass. Using a straight edge and a compass, one can construct various geometrical figures and carry out certain operations on geometrical figures. For instance, given two points, the line through these points can be drawn. Given a line and a point not on the line passing through the point and perpendicular to the line can be constructed. There were, however, three constructions which the ancient Greek mathematicians were unable to carry out. The first was trisecting the angle. This means, given an arbitrary angle, trisect the angle into three equal subangles. The second was called doubling the cube. Given a cube, construct the edge of another cube with twice the volume of the original cube. And the third was squaring the circle. Given a circle, construct a square with the same area. Doubling the cube, the most famous of the collection, is often referred to as the Dahlian Problem. According to legend, the citizens of the Greek island Delos in 430 BC consulted the oracle at Delphi in hopes of stopping a plague ravaging their island. The oracle told them that they needed to double the size of their altar to the god Apollo that had the form of a cube. While mathematicians at the time were apparently able to complete this task using mechanical methods, they were not able to do so using pure geometry. It was not until the 19th century that mathematicians proved, using algebraic methods, that each of these three constructions is impossible using only a straight edge and compass. Before getting started, we need to make sure we understand what we mean by a straight edge and compass. To begin with, a straight edge is not a ruler. That is, there are no measuring marks on the straight edge. So the straight edge can be used only for drawing a line through 2 points or to extend an existing line segment. However, the straight edge is assumed to have an arbitrarily long length. When using the compass, we can place the center at any point and can draw a circle or circular arc passing through another point. Originally, the compass was assumed to collapse when lifted from the page, so could not be used to transfer distances from 2 points to another location on the page. Modern compasses remain open to a fixed distance when lifted from the page. It can be shown, however, that any construction that can be carried out with using a modern compass can also be done using a collapsing compass. This result is called the compass equivalence theorem. The following are some of the constructions that can be carried out using only a straight edge and compass. First, given a point P and a line L, we can construct a line perpendicular to L and passing through P. Second, given a line L and a point P not lying on L, we can construct a line parallel to L and passing through P. Third, given a point P, a line L passing through P, and a constructible number R, which we'll discuss later, we can construct a point Q on L so that the length of the line segment PQ is the absolute value of R. We'll need to use some results from geometry in order to prove that our constructions actually do what we claim they do. In particular, we'll use results about congruent and similar triangles. Two triangles are congruent provided their corresponding sides are equal in length and their corresponding angles are equal in measure. Two triangles are similar provided their corresponding angles are equal in measure. And we have a couple results regarding congruent and similar triangles. The first is called the SSS theorem. Two triangles are congruent if the sides of one are congruent to the corresponding sides of the other. And the second is called the SAS theorem. Two triangles are congruent if any pair of corresponding sides and their included angle are congruent. And for similar triangles, we know that corresponding sides of similar triangles are proportional. So if one triangle has sides A, B, and C, and the other has corresponding sides A prime, B prime, and C prime, then A over A prime equals B over B prime equals C over C prime. While it's impossible to trisect an arbitrary angle, we can bisect an angle, as shown in our first example. So for this example, we want to bisect the angle QPR, shown. So we'll start by drawing a circular arc with center P crossing the legs of the angle. Next, let S and T be the points where the arc intersects the legs. Now draw the line segment ST joining S and T. and we can erase the arc at that point. Next, draw two circular arcs with centers at S and T and radius the length ST. And let U be the point where these two arcs intersect. Then draw the line segments SU and TU. And finally, draw the line segment PU. Now we want to prove that the line segment PU bisects the angle QPR. And from the construction, we know that the length of the line segment PS is equal to the length of the line segment PT, and the length of the line segment SU equals the length of the line segment TU. It follows that the two triangles PSU and PTU have congruent sides, so by the SSS theorem are themselves congruent. This then implies that the two angles, angle SPU and angle TPU, are congruent, and thus PU bisects the angle QPR. We can use the angle bisection construction to construct a line perpendicular to a given line passing through a point not on the line. So given a line L and a point P not on the line, we want to construct a line perpendicular to L and passing through P. So we'll start by drawing a circular arc with center P crossing the line L in 2 points, and draw the line segments from P to the 2 points Q and R. Next, bisect the angle QPR, and let O be the point where the angle bisector intersects L. We now want to show that the line segment PO is perpendicular. By the construction, the length of PQ is equal to the length of PR, and the angle OPQ is equal to the angle OPR. Since the two triangles, OPQ and OPR, share the side OP, then they have two congruent sides with their included angle also congruent. It follows by the SAS theorem that the triangles OPQ and OPR are congruent. And this implies that the angle POQ is equal to the angle POR. Since these two angles sum to 180 degrees, they must each equal 90 degrees. And thus the line PO is perpendicular to L. Now, in order to determine whether or not a construction is possible, we want to translate the geometric problem to an equivalent algebraic problem. As we'll see, constructions involving a straight edge correspond to solutions of linear equations, while constructions involving a compass correspond to solutions of quadratic equations. To obtain an algebraic description of straight edge and compass constructions, we start with 2 points, the origin O of a rectangular coordinate system, and the point P with coordinates 1, 0. We can then draw the line OP passing through these 2 points, and the circles with centers at O and P with radius OP. These circles determine new points where they intersect the line OP and each other. We can then draw a line passing through any two of the points, or a circle with center at any point passing through any other point. These will determine new points where they intersect existing lines or circles. And repeating this process, we can construct more and more points. Next, we want to define constructible points and numbers. So a constructible point is any point that can be constructed in a finite sequence of steps, starting with the points O and P equal 1, 0, and drawing lines passing through previously constructed points, or circles centered at a previously constructed point passing through another previously constructed point. A constructible line is a line passing through two constructible points. A constructible circle is a circle centered at a constructible point with radius equal to the distance between two constructible points. A real number r is a constructible number provided that the point r0 is a constructible point. First note that the point r0 is constructible if and only if the point 0r is constructible. And to prove this, well, this is a biconditional, so we'll start with the forward direction. So suppose the point R0 is constructible. We need to show that the point 0R is constructible. So starting with the origin O and the point R0, we can draw the x-axis and y-axis. Next, we can draw a circular arc with center O passing through R0. This arc will intersect the y-axis in the point 0R, so this point is constructible. And this is the point 0R. And the proof of the backward direction will be similar. For a second remark, a point RS is constructible if and only if its coordinates R and S are each constructible numbers. So to prove this, for the forward direction, we suppose the point RS is constructible. We need to show that each of the coordinates R and S are constructible numbers. So we'll start with the point RS and the x and y axes. From the point RS, we can draw the lines passing through the point and perpendicular to the x-axis and perpendicular to the y-axis. These will intersect the axes in the points R0 and 0S, showing these points are constructible. And since R0 is constructible, then by definition R is a constructible number. And since 0S is constructible, then by the previous remark S0 is constructible, which implies S is constructible. And the proof of the backward direction will be similar. Now it's clear that every integer is constructible. In fact, it follows from our first theorem that every rational number is constructible and that the set of constructible numbers forms a subfield of R. So this is theorem 15.1. And what it says is, let A, B, C, and D be constructible numbers with C not equal to 0 and D greater than 0. Then each of A plus B, A minus B, A times B, A divided by C, and the square root of D is a constructible number. To prove this, first note that since A is constructible, then A0 is a constructible point. And by drawing a circular arc centered at the origin passing through A0, we can construct the point minus A0, which shows that minus A is constructible. This means we can assume that the numbers are all positive, because if A is constructible, then minus A is constructible. So we want to first show that A divided by C is constructible. Since A and C are constructible, then the points capital A equal A0 and capital C equal 0C are both constructible. So we'll start with a drawing containing those 2 points and the origin. And so the line L passing through these points is also constructible. Then the line passing through the constructible point I equals 0, 1, parallel to L, is constructible. And suppose this line intersects the x-axis at the point P equal x0. Then x is a constructible number, and the triangles OPI and OAC are similar, which implies that x divided by A is equal to 1 divided by C. And solving for x, we obtain x is equal to A over C. And therefore A over C is a constructible number. So this shows that the quotient of 2 constructible numbers is constructible. Next, we want to show that the product AB is constructible. In the case that B is equal to 0, then AB equals 0, which is constructible. We can then assume that B is not equal to 0. The proof that the quotient of 2 constructible numbers is constructible implies 1 over B is constructible, and hence A times B, which is A over 1 over B, will be constructible, again using the fact that the quotient of 2 constructible numbers is constructible. To show that A plus B and A minus B are constructible, the sum and the difference of 2 constructible numbers is constructible, we can draw a circular arc with center at A0 and radius B, and this will intersect the x-axis at A plus B, 0, and A minus B0. And this shows that both of those numbers are constructible. Finally, to show that square root of d is constructible, we'll start with the origin O and the point I equal 1, 0. Since d is constructible, then we can construct the point capital D equal d plus 1, 0. And we can construct the midpoint A of the line segment OD. This is a simple geometric construction. Draw the circle with center A and radius d plus 1 over 2, passing through O and D. We'll only need the top half of the circle, so we'll draw it in as a semicircle. And then draw the line perpendicular to the x-axis passing through I. And suppose this line intersects the upper half of the circle at the point B with coordinates 1, y. We want to show that y is equal to square root of d. So we'll start by drawing the line segments OB and BD. And by a theorem from geometry, the angle OBD, since it is inscribed in a semicircle, is a right angle. And then the triangle OBD is a right triangle, which implies that the sum of its acute angles, so angle OBI plus angle IBD, add up to 90 degrees. Since OIB is also a right triangle, then the sum of the angles in OIB, OBI plus IOB add up to 90 degrees, which is, as we just said, the sum of the angles OBI and IBD. Well, angle OBI appears on both sides of this equation, so this implies that angle IOB is equal to angle IBD. Now, since triangle BID is also a right triangle, then the sum of its acute angles add up to 90 degrees, so that's angle IDB plus angle IBD equals 90 degrees. And again, this is equal to the sum of the angles OBI plus IBD. And angle IBD appears on both sides of this equation, so this implies that angle IDB is equal to angle OBI. So these two equalities show that triangles OIB, that's the small right triangle on the left half of the semicircle, and triangle BID, that's the larger right triangle on the right half of the semicircle, are similar. And using the property that corresponding sides of similar triangles are proportional, we can say that the length of ID divided by the length of IB is equal to the length of IB divided by the length of OI, which is d over y is equal to y over 1. And therefore y squared equals d, so y is equal to the square root of d. And since y is constructible, then it follows that square root of d is constructible. And this completes the proof of the theorem. Now the following two corollaries follow directly from the theorem. The first is corollary 15.2, which states that every rational number is constructible. So to prove this, first note that the theorem implies that the sum of any two constructible numbers is constructible. And since 1 is constructible, this implies that every positive integer is constructible. And the theorem also implies that the quotient of any two constructible numbers is constructible. And since every positive integer is constructible, this implies that every positive rational number is constructible. And since a number r is constructible if and only if minus r is constructible, it follows that every rational number is constructible. And this proves the corollary. For our second corollary, the set of constructible numbers is a subfield of R. To prove this, well, first note that the theorem implies that the set of constructible numbers is closed under subtraction and multiplication, so is a subring of R. And furthermore, for each constructible number c not equal to 0, 1 over c is constructible, which implies the set of constructible numbers contains multiplicative inverses for each non-zero element. And this shows that the set of constructible numbers is a subfield.